Artificial intelligence has a networking problem. The world is building larger GPU clusters, larger data centers, and increasingly powerful computing systems. But all of those processors must constantly exchange enormous amounts of data. If the network connecting them is too slow, expensive, or power-hungry, even the most advanced AI chips can spend valuable time waiting. Now China says it has completed a major test of a technology designed to attack that bottleneck. Yangtze Optical Fiber and Cable, better known as YOFC, worked with China Telecom and optical equipment company Decoli to transmit 51.3 terabits of data per second across 206.5 kilometers, or roughly 128 miles. The system reached as much as 2 terabits per second on a single wavelength, and it completed the entire distance without electronically regenerating the signal or using remotely pumped amplifiers along the route. But the most unusual part was the cable. Instead of sending light through a conventional solid glass core, the system used hollow core fiber. Most of the light traveled through an air-filled channel surrounded by a carefully designed glass structure. That allows optical signals to move faster and experience far less interaction with the glass itself. YOFC says its technology can reduce latency by approximately 31%, increase optical propagation speed by around 47%, and sharply reduce nonlinear distortion. The question is whether this is simply another impressive telecommunications demonstration, or whether air-filled fiber could become a critical part of the infrastructure connecting the world's largest AI systems. Why normal fiber uses glass? Modern communications depend on fiber optic cables. Internet traffic, cloud services, financial transactions, video streaming, mobile networks, and data center connections all rely on pulses of light, traveling through extremely thin strands of glass. Traditional optical fiber contains a solid core made primarily from silica. That core is surrounded by another layer of glass with different optical properties. The structure keeps light confined inside the cable as it travels across long distances. This technology transformed global communications because fiber can carry vastly more information than copper while losing relatively little signal strength. But conventional fiber still has physical limitations. Light does not travel through glass at the same speed that it travels through a vacuum or through air. The refractive properties of silica slow the signal down. In ordinary fiber, optical propagation is typically around 2/3 of the speed of light in a vacuum. That delay may sound insignificant, but over hundreds or thousands of kilometers, microsecond accumulate. For ordinary video streaming, the difference may not matter. For distributed artificial intelligence clusters, financial trading, cloud infrastructure, or scientific computing, small delays can affect performance. Glass also interacts with intense optical signals. As more power and more data channels are pushed through the same fiber, nonlinear effects can distort the signal and limit how much information can be transmitted reliably. Hollow core fiber attempts to avoid those problems by moving most of the light away from solid glass. How hollow core fiber works, the name can be misleading. Hollow core fiber is not simple, an empty plastic tube. It is still an advanced glass structure, manufactured with extremely precise geometry. Around the air-filled center are thin glass membranes or tubes, arranged to keep light trapped inside the hollow region. The structure reflects and guides the optical signal through the air-filled core, while allowing only a small portion of the light to interact with the surrounding material. Because the light travels primarily through air, it can move significantly faster than it does through solid silica. The lower interaction with glass also reduces several types of distortion. This can allow engineers to send stronger optical signals, use more advanced modulation, and potentially increase the distance between major network equipment. The concept is not completely new. Researchers have studied hollow core fiber for decades. The problem was loss. Early designs allowed too much light to leak out of the core. A signal weakened so quickly that the lower latency was not enough to justify the technology. Conventional fiber remained cheaper, easier to manufacture, easier to connect, and more reliable over long distances. The important change is that hollow core attenuation has been falling. YOFC says its latest fiber has achieved loss as low as 0.04 decibels per kilometer under reported test conditions. That is a critical milestone because low latency only matters commercially if the signal can also survive a useful distance. What China's trial achieved, the new Chinese trial combined high capacity, long distance, and a real cable deployment. The system transmitted an aggregate 51.3 terabits per second across a 206.5 kilometer hollow core fiber span. Aggregate capacity means the total data rate across multiple wavelengths. It does not mean one optical channel carried all 51.3 terabits. The maximum reported rate for an individual wavelength was 2 terabits per second. Different colors or wavelengths of light can travel through the same fiber simultaneously. This technique is called wavelength division multiplexing. Each wavelength carries its own stream of information. When many channels are combined, the fiber can transport an enormous total volume of data. The companies used a self-developed optimization system to adjust the data rate and optical power of individual wavelengths. That matters because not every channel experiences exactly the same conditions. Rather than forcing every wavelength to operate at one fixed setting, the system could allocate resources more efficiently. The result was a very high total capacity across a long, hollow core span. What without repeaters really means, some headlines have suggested that the trial required no signal boosting. That is not completely accurate. The system used conventional erbium-doped fiber amplifiers, commonly called EDFAs. These devices amplify optical signals without first converting the information into an electronic form. What the system avoided was signal regeneration along the 206.5 kilometer span. A regenerator receives a weakened optical signal, converts it into electrical data, cleans and retimes that data, and then creates a new optical signal for the next section of the journey. Regeneration can extend network reach, but it adds equipment, power consumption, cost, latency, and potential failure points. The trial also avoided remotely pumped amplifiers placed at difficult locations along the cable route. So the achievement is not that the light traveled completely unassisted. The achievement is that the companies maintained a 51.3 terabit per second connection across the full span using optical amplification without needing intermediate electronic regeneration. That makes the result far more relevant to real long-distance networks. Why this matters for AI. An AI cluster is not just a room full of processors. It is a networked system. During model training, thousands of accelerators repeatedly exchange gradients, parameters, activations, and other information. The processors must remain synchronized. If communication takes too long, expensive hardware can sit idle while waiting for data from another machine. Inside one server, this problem is addressed through extremely fast chip-to-chip connections. Inside one rack, specialized realized networking connects multiple systems. But the AI industry is increasingly moving beyond individual racks and even beyond individual buildings. Power availability may force companies to divide computing infrastructure across several data centers. One location may not have enough electricity, cooling capacity, or physical space to contain an entire cluster. Distributed AI infrastructure therefore needs high-capacity connections between separate buildings or regions. This is where hollow core fiber may become valuable. Lower propagation latency could help distant data centers behave more like one coordinated computing system. Lower optical nonlinearity could allow stronger signals and more data channels. Longer spans without electronic regeneration could reduce network complexity and energy use. Hollow core fiber will not make a slow network switch faster or improve poorly designed software. but it could improve the physical layer carrying information between major computing facilities. The energy question. AI data centers are already placing enormous pressure on electrical grids. The processors consume power, cooling systems consume power, memory and storage consume power, and the networking equipment connecting everything also consumes power. Long-distance optical systems require amplifiers, transponders, switches, and sometimes regenerators. If hollow core fiber allows longer distances between regeneration points, operators may be able to remove some equipment from a network route. That could reduce power consumption, maintenance requirements, and physical infrastructure. However, the total savings will depend on the complete network. A faster fiber does not automatically make every attached device more efficient. Receivers still consume energy. Switches still process traffic. Cooling is still required. Installation costs may also remain high. The strongest case for hollow core fiber may initially appear in networks where latency and capacity are more valuable than the lowest possible cable price. The global race. China is not developing hollow core fiber alone. Microsoft acquired British hollow core specialist Lumina City and has been deploying the technology in parts of its Azure infrastructure. Microsoft has also worked with manufacturing partners to expand production. Researchers associated with Lumina City and the University of Southampton have demonstrated hollow core designs with losses below some long-standing solid core fiber benchmarks. Amazon and other major cloud companies have also examined advanced fiber technologies as data center networks expand. This means the Chinese trial should not be interpreted as proof that China invented the entire field or has permanently defeated Western competitors. It shows that China is building its own manufacturing, deployment, and optical equipment ecosystem around the technology. YOFC says it has established an integrated production chain covering preform manufacturing, fiber drawing, coding, cabling, and testing. The company has also produced a continuous hollow core fiber length exceeding 90 kilometers and participated in multiple pilot or commercial projects. That manufacturing capability may become as important as laboratory performance. A fiber technology cannot transform global networks if it can only be produced in short, fragile pieces. The manufacturing challenge. Conventional fiber has decades of industrial experience behind it. Manufacturers can produce enormous quantities at low cost. Telecommunications companies understand how to install it, splice it, test it, and repair it. The supporting standards and equipment are mature. Hollow core fiber must compete with that entire ecosystem. Its internal geometry is far more complex. Small manufacturing defects can increase optical loss. Joining two hollow core sections can be difficult because the air-filled structures must remain precisely aligned. Connections with conventional fiber can also introduce additional loss. Bending, cabling, environmental stress, and long-term reliability must be carefully tested. A record achieved on one route does not prove the same performance can be reproduced cheaply across millions of kilometers. Operators also need compatible amplifiers, transceivers, connectors, monitoring equipment, and installation procedures. This is why hollow core fiber is unlikely to replace all conventional fiber in the near future. Traditional silica fiber is already extremely effective for most communications. It is inexpensive, reliable, and widely available. Hollow core technology will probably enter the market first, where its unique advantages justify the added cost, where it could be used first. The most obvious early applications are financial networks, major cloud regions, AI data center links, scientific facilities, and telecommunications backbones. High-frequency trading companies pay large amounts of money to reduce network latency by tiny fractions of a second. Cloud providers may value faster communication between separate data centers. AI companies may need to connect clusters located near different power sources. Scientific institutions may use the fiber to transfer enormous datasets or synchronize precision instruments. Military and government networks could also value lower latency and reduced signal distortion. Consumer broadband will probably not be the first major market. Replacing the fiber entering individual homes would be expensive, and most household internet connections are limited by service plans, routers, Wi-Fi, and network congestion rather than the propagation speed of the glass itself. The technology makes more sense in the backbone of the network, where enormous quantities of data travel across long distances. My take is that this trial is important, but not because conventional fiber is suddenly obsolete. Solid core silica fiber will remain the foundation of global communications for many years. It is proven, inexpensive, and good enough for an enormous range of applications. The breakthrough is that hollow core fiber is moving out of small laboratory experiments and into longer commercial scale links. China's 3 terabit per second trial demonstrates that an air-filled core can support high-capacity transmission across more than 200 kilometers without electronic regeneration along the span. That is a meaningful engineering result. The technology still faces manufacturing costs, splicing challenges, standardization questions, and competition from improving conventional fiber. But AI is changing the value of network performance. When companies spend billions of dollars on processors, memory, and data centers, the cost of a better cable becomes easier to justify if that cable keeps the entire computing system operating more efficiently. The next AI bottleneck may not be the chip. It may be the connection between the chips. And China has just demonstrated a fiber designed to move that data through air instead of solid glass. So what do you think? Could hollow core fiber become the next major upgrade to global AI infrastructure? Or will manufacturing complexity keep it limited to specialized networks? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the future of computing will not depend only on how fast processors can calculate, it will also depend on how quickly information can move between them.